Welcome to this video on wave functions. Today, we will explore what a wave function is, its connection to trigonometric identities, how to find maximum and minimum values, solving equations involving these functions, and finally, look at some exam-style questions. The wave function allows us to express a combination of sine and cosine waves, like a cos x plus b sine x, as a single k cos of x plus or minus alpha, or k sine x plus or minus alpha function. These shapes describe various phenomena, including sound, light, and electrical waves. The general shape of y equals sine x plus cos x is similar to a sine or cosine wave, but shifted left or right and with a different vertical height, as illustrated by the graph on screen. In general, adding sine and cosine functions allows for a transformation into a related single sine or cosine expression. By determining the constants k and alpha, we can make the expression on the right equal to the one on the left for all values of x. Let's look at a worked example. We want to write 4 cos x plus 3 sine x in the form k cos of x minus alpha. By expanding this and equating the coefficients of cos x and sine x, we create a pair of simultaneous equations to solve for k and alpha. To solve these equations, we square and add the two equations to find k. Then, we determine alpha using the tangent ratio, paying close attention to the signs of the sine and cosine components to place alpha in the correct quadrant. Continuing our example, we find that equals 5. The angle alpha is 36.9 degrees, placing it in the first quadrant. Therefore, 4 cos x plus 3 sine x can be expressed as 5 cos of x minus 36.9 degrees. Here is another example, writing cos x minus root 3 sine x in the form r cos of x plus alpha. We expand the expression, equate the coefficients, and solve the simultaneous equations for r and alpha. After calculating, we find r equals 2 and alpha is 60 degrees. Finally, we can write our original expression as 2 cos x plus 60 degrees. For our third example, we write 5 cos 2x plus 12 sine 2x in the form k sine 2x plus alpha. Following our standard method, we expand, equate coefficients, square, add, and use the tangent ratio to determine k and alpha. The calculation gives us k equals 13, and alpha is 22.6 degrees in the first quadrant. The final expression is 13 sine 2x plus 22.6 degrees. Now let's address finding maximum and minimum values. Given the expression sine x minus cos x, we first write it in the form k cos of x minus alpha. Then identify its maximum and minimum values and the corresponding values of x. First, we convert the expression to root 2 cos x minus 135 degrees. Through our steps of equating coefficients and calculating, we determine k is root 2 feet and alpha is 135 degrees. For the maximum value, we look at the graph of root 2 cos x minus 135 degrees. The maximum occurs when the cosine term is 1, which happens when the angle is 0, giving us a maximum value of root 2 feet at x equals 135 degrees. Similarly, the minimum occurs when the cosine term is -1, which happens at an angle of 180 degrees. This results in a minimum value of negative root 2 feet at x equals 315 degrees. Let's apply these principles to our first example, a synthesizer combining two sound waves. We have a first wave, v equals 75 sine t, and a second wave, v equals 100 cos t. We need to find the minimum value of their resultant wave. First, we express the resultant wave in the form k sine t minus alpha. By comparing coefficients, we determine that k will be 125, and we'll need to find the value of alpha in the fourth quadrant. Using our trigonometric identities, we find the angle alpha to be approximately 306.9 degrees. This confirms our resultant wave is 125 sine t minus 306.9 degrees. To find the minimum value, we know the minimum of the sine function is -1. Therefore, the minimum value of our resultant wave is -125. The minimum occurs when the sine component equals -1, which is at 270 degrees. Solving for t, we find it occurs at 216.9 degrees, after accounting for the wave shift. Visualizing this on a graph, we can see the sine wave shifted to the right, with the minimum point clearly marked at our calculated value of t equals 216.9 degrees. Next, let's explore solving trigonometric equations. We want to solve root 3 cos x plus sine x equals root 2 feet for values between 0 and 2 pi. Step 1 is to write root 3 cos x plus sine x in the form k cos of x minus alpha. By expanding and comparing coefficients, we can solve for k and alpha. Solving these coefficients, we find that k equals 2. We then determine alpha by looking at the tangent ratio of the components, which leads us to an angle of 30 degrees. Now that we've rewritten our equation as 2 cos x minus 30 degrees equals root 2 feet, we can simplify this to cos x minus 30 degrees equals root 2 over 2 feet. Solving for the angle x minus 30 degrees, we find it must be 45 degrees or 315 degrees. Adding 30 degrees to these values gives us our final solutions for x. Moving to a more complex exam-style question, we consider a builder constructing a gable end in the shape of an isosceles triangle atop two squares. The goal is to show the area A of the gable end can be expressed as a function of the angle theta. We start by assigning S as the side length of the squares. We express the area of the squares and the triangle separately, then combine them to reach the final area formula, which involves our trigonometric functions. In the final part, we solve for theta when the total area is 30 square meters. By applying the wave function method, we reduce the complex equation to a solvable form, completing the problem. Welcome to this video on wave functions. We will work through several exam-style questions to build your confidence, covering techniques for identifying constants and solving trigonometric equations. Let's begin with a question requiring us to express 2 sine x plus 5 cos x in the form k sine of x plus a. We'll expand the expression, equate the coefficients, and solve for k and a. We also need to find the coordinates of the minimum turning point, P. Next, we tackle sine x cos x. We need to express this in the form k sine x a and then sketch the graph, highlighting the maximum and minimum values, as well as the x and y-axis intercepts. For our third problem, we will express cos x plus sine x in the form k cos of x plus a. This will involve the usual steps of expanding, equating coefficients, squaring, adding, and dividing to find the constants k and a. In this next task, we express a given function in terms of r cos x a and then find its maximum value. We must also determine the specific value of x within the interval 0 to 2 pi, where this maximum occurs. This question asks us to express a specific trigonometric function in the form k sine x a. Once we have found the constants, we will solve the resulting equation for x within the given range. Here we have a diagram showing an incomplete graph. Our task is to find the coordinates of the maximum stationary point by using the properties of the sine and cosine functions and their combined waveform. We are now working with a function f of x. We need to express this in the form k cos x a, and then use this result to solve the equation algebraically for x within the specified interval. In this final example, we solve simultaneous trigonometric equations. We'll simplify the system using the relationship between sine, cosine, and tangent, and then determine the solution in the correct quadrant. Finally, we address another equation requiring the r cos x a form. We will perform the necessary substitutions and calculations to isolate x and find all valid solutions within the range 0 to 360 degrees. You have now completed all 9 questions in this series. By practicing these techniques, you'll be well prepared to handle wave function problems in your assessments. Keep practicing your trigonometric identities.